All right, now we want to talk about something called a fictitious force. Fictitious or false force. So before we do that, we need to talk about something called a reference frame. So, like right now, this room is our reference frame. If we were in a jet, the jet would be our reference frame. So, all right, that kind of makes sense? So you're doing your experiment in some kind of reference frame. If I were in a car driving 60 miles an hour relative to the road, like on H1 or something, the car would be my reference frame. If somebody was standing still on H1, that would be his or her reference frame. If you were passing me, your car would be your reference frame. Okay. Now, Newton's laws, which is what we are learning in Physics 105, they only work with non-accelerating reference frames. All right? Non-accelerating reference frames. And we'll talk a lot more about that in Physics 106 when we talk about special relativity. Okay, can you read that? Yeah, sort of. All right, so pause your video and figure this out. Okay, so let's do it. You are a passenger in a car. You're not wearing your seatbelt. So let's say you're in the front, okay? So passenger side, not wearing your seatbelt. Without increasing or decreasing the speed, the car makes a sharp left turn, and you find yourself colliding with a right-hand door. Yep, that makes sense, right? That's our experience. Which is the correct analysis of the situation? So what do they mean? What's the correct analysis? The correct analysis is looking at this from a non-accelerated reference frame. Well, come on. You're in a car. You're making a turn. So you are an accelerating reference frame. So we don't want to analyze this from your point of view because you're in an accelerated reference frame. So, well, what or who is in a non-accelerating reference frame? Well, let's just pretend there's a drone up there and it's stationary and it's looking down, okay? So what would that drone see? Okay, this is what right? So look, Newton's laws say if there's no forces, you just keep going straight. But you're making a turn, right? So this is what the drone would see. So the drone, let's say the drone is a person, right? So the drone sees you going left around the circle. So the drone says, hey, there has to be a force pointing towards the center of the circle. See, the drone paid attention. So what is that force? It's a normal force, right? So let's read this. You try to keep moving straight, but what prevented you from going straight? The door, right? The normal force that the door exerts on you. So the door provides the center-directed force that makes you move in a circle. So that is the correct analysis. Starting at the time of collision or turn, the door exerts a leftward force on you. Okay? Now, but come on! How do you feel? Right? How do you feel? You feel like something's shoving you out there, right? But again, that's from an accelerating reference frame. Newton's laws don't work in accelerating reference frames, okay? So we will never discuss those forces, okay? In other words, I know you feel like something is pushing you out there, but it's not valid because it's in an accelerating reference frame. So we call those forces fictitious, and we'll never talk about them again. There. The end. All right? Okay. All right. Now we want to talk about non-uniform circular motion. And I'm sorry, there's going to be some more in a later chapter. Whatever. All right? So now, what's non-uniform circular motion? So now, it's like the speed is changing, right? Maybe it's going, forget it. I'm sober. All right, okay? So, and what we want to do vertical non-circular motion, okay? So, all right, so yeah, here's what we want to do. All right, so we have been hired. So this guy is Evel Knievel. If you've never heard of Evel Knievel, he was a stunt person. I don't know if he's alive. Let's say he is a stunt person. But anyway, so he's this crazy guy who does all these stunts. And he's like broken nearly every bone in his body. He does all these crazy things. You know, like there was one time he had all these school buses lined up. I mean, tons of them. And then he had a ramp, and he uses a motorcycle, and he jumped over all these school buses. I mean, he does all sorts of crazy things. But anyway, so let's say that we were hired by this guy, Evel Knievel. And we're supposed to do the physics, and we're supposed to tell him how fast he has to go in order to complete this circle. Okay? So what does it mean to complete the circle? That means that the tires have to maintain contact with this track the entire way, right? Because, you know, if they don't maintain contact, then he's dead, or he's going to be hurting for certain, you know? So that's what we want to do, all right? Now remember, circular motion. So what do we care about? Centripetal forces. Forces that point towards the center of the circle. So what are the only centripetal forces? Well, you know, weight and normal, right? What else is there? You know, just weight and normal. Now, are the normal forces always the same? What do you think? No way, right? Here, he's pressing down a lot on the track. Here, you know, he's not pressing very much at all, right? So the normal forces are not constant. Okay, so let's draw the centripetal force diagram. Let's just concentrate on 1 and 2, because that's the exciting part, right? I mean, this is the exciting part. So let's draw the centripetal force diagrams. Okay, now remember I told you that the sum of the forces equals mv squared over r, and I told you that sometimes it's going to be more than 1. Well, here we have it, right? Here we have it. So right here, so this is a centripetal force. Now this is too, but it's with a negative sign. These are, right, because this doesn't point towards the circle, this points away from the circle, so we're going to give it a negative sign. These both point towards the center of the circle, so those are both positive. All right, so let's do it. All right, so this is the force diagram. By the way, why does this normal force have to be greater than this weight? Well, there has to be a centripetal acceleration, right? So this has to be bigger than that for there to be a net force up there. Okay, so let's do it. Okay, let's do number 1 first, the ground. Okay, so at the ground, the sum of the centripetal forces, which equals mv1 squared over r. I'm going to put a 1 here because I want to differentiate the velocity here from the velocity here. Okay, so what is it? Okay, now I don't know why, but they use uppercase N, so I'll just follow it. So N1 points towards the center of the circle, but mg points away from the center of the circle, so we give it a negative sign, minus mg. Okay? So you got to be careful, right? If it points away from the center, you put a minus sign. All right, so therefore, what's N1? So N1 equals mv1 squared over r plus mg. So it's going to be big, which is kind of what you expect. By the way, what is this called? So what's this N called? We learned about it a while ago. Apparent weight. Remember we talked about apparent weight? So that's the apparent weight. Okay, wonderful. But now let's do 2, because 2 is what we're getting paid for, right? We want to make sure Evel Knievel maintains contact. So that's what we care about. So 2, we write the sum of the centripetal forces equals mv2 squared over r. And now they both point towards the center of the circle, right? So now we just say n2 plus mg. And therefore, n2 equals mv2 squared over r minus mg, right? Minus mg. All right. Now here's the important thing. We want, I mean, again, like I said earlier, we want the tire of the motorcycle to maintain contact with the track. So that means we want N2 to be a positive number, right? What would happen if N2 were 0? Then there's no contact, which is not a good thing, right? Okay, so in order to maintain contact, you know, wheel with track, we require N2 to be bigger than 0. All right, now look, what does N2 depend on? You know, it depends on the mass, right, of the Evel Knievel with his motorcycle. Depends on the radius of the turn, and look at it. It depends on the speed in a big way, because it's v squared, right? V squared, okay? All right, so let's do this. Find the minimum speed for the motorcycle and Evel Knievel to remain on the track at position 2. The minimum speed. So this is what we're getting paid to figure out, because we're the consultant. Okay, so the minimum speed is going to be when it's just barely greater than 0. Of course, we're not going to, you know, we're going to tell them to go faster than that. But anyway, so let's do it. Okay, so basically, if N2 is 0, then he just lost contact, right? Right? Okay, so what we want this to be greater than 0. Well, look at this. If we want this to be greater than 0, that means mv2 squared over r has to be greater than mg. So we want mv2 squared over r greater than mg. Now, look, this is incredible. Cancel the m's. So therefore, v2 is greater than gr. Of course, we got a square root, right? I skipped a step, hope you don't mind. Right? So multiply both sides by r, take the square root. So there you go. So the velocity at the top of that ring, or whatever, has to be greater than gr. Simple as that. And it doesn't depend on mass. We've seen that again and again and again, right? So there you go. You just tell them, hey, make sure you're going faster than that, piece of cake. Now, have you ever seen the demonstration where somebody has a bucket of water, then they tie a piece of rope to the bucket, and they go like this, and the water doesn't fall out? It's pretty much the same analysis. I mean, similar analysis. So there you go. Okay, let's completely, make sure you know how to do this, by the way. I think this is kind of important, so you should probably, well, you should expect to see it on an exam, something similar to that. All right, let's shift gears and talk about circular orbits. All right, so a while ago we did projectile motion, right? Projectile motion was when you just throw something. Okay, now when we studied projectile motion, we assumed a flat Earth, because, you know, we weren't throwing things very far, right? Well, now we're not going to include that assumption anymore. So we're going to have a spherical Earth, okay? A spherical Earth. Now, so here, look at D. So D is like a communication satellite. It orbits the Earth, doesn't crash into the Earth, right? It doesn't crash. So what's so different about A, B, C, and D? I mean, let's just talk about it. Like A, you know, if I was at the top of a building, height h, if I threw something, you know, what would it do? It would go like this, right? And then let's say I threw it even faster. Well, then it would just go further, but it would still go like that. And then let's say I threw it even faster. So then it would kind of go, you know, like that, all right? So what I'm saying is, if the first time I throw it, not so much force, it's kind of going slowly, it just goes like this. Then the second time I throw it more force, it goes like this, because it's going faster, right? Third time it's going even faster, it goes like this, but they still eventually crash into the Earth. But there's a certain speed where it goes all the way around, right? All the way around, right? So let's talk about that. Okay, so basically, this is too slow, this is too slow, this is too slow. D has the correct speed to make it all the way around the Earth. And that's what we want to figure out. And look at it, circular motion, right? So we can do it. Okay, now we're going to make an assumption, which we'll ignore later on. We're going to assume that the satellite is very, very close to the surface of the Earth. Okay? All right, here we go. So communication satellites do not crash into the Earth because they have the correct speeds to maintain their circular orbits. What is this speed? Assume the satellites are very close to the Earth. Well, circular motion, what do you write down? You don't even think about it anymore, hopefully, right? As soon as you see circular motion, you write it down. Okay, but then you got to answer the question, okay, well, what are the centripetal forces? Now here there's only one, and what is it? It's gravity. And look at, if we're close to the surface of the Earth, what's gravity? Just weight, mg. So therefore, just do the math, right? We're trying to solve for velocity. Notice what cancels. Masses cancel. And we get V equals gr. V squared equals gr. So V equals the square root of that. There you go. So if the Earth were a perfectly smooth sphere, and you stood on top of a big box or something, and you threw something at that, greater than this speed, at this speed or greater, it would circle the Earth. Now, wait a second. What kind of motion is this? What's the only force acting on it? Gravity. So this is free fall or projectile motion. It's free fall, sorry. It's free fall. And what did we learn about free fall? Independent of mass. This is independent of mass, right? So that means you could throw a car, if you're that strong, or you could throw an eraser. Again, we're ignoring air resistance. You could throw anything. As long as you had the right speed, it would circle the Earth. All right. Very cool. Now, again, this was easy because, we said we were close to the Earth, So we just said that the gravitational force was mg. Well, let's get a little bit more sophisticated. You've seen this before. This is called Newton's law of gravity. So the gravitational force between, say, the Earth and the Moon is this gravitational constant, a small number, times the mass of the Earth, times the mass of the Moon, divided by the distance between the centers, squared. Okay? All right. Now, we already did this. Let's just do it again. We did this in chapter 5. What's the force of gravity between you and the Earth? Well, right, G, M, Earth, MU. And what's the distance between the center of the Earth and the center of U? It's basically the radius of the Earth squared. Remember that? And again, this is equal to your weight. All right, your weight. So mu times g. So therefore, what's little g? We can cancel the mu's, and that's little g. All right, we already did that. Okay, but notice, little g only depends on the characteristics of the Earth, right? This is the constant, this is the mass of the Earth, and this is the radius of the Earth squared. So you could do a similar analysis for the Moon or for any planet you felt like it. All right, very nice. So, let's say you're on planet X, whatever that is. what is G for this planet? Okay? Well, just do what we just did, you know. So the force of gravity is G, the mass of planet X, the mass of planet U, divided by the radius of planet X squared. And again, that's equal to your weight, which is mass of U times G. So we're trying to find little gx. Oh, sorry, I can put a little x here. All right. So you see that as before, the mass of U cancels, and the acceleration due to gravity on planet X is G, mass of the planet X, divided by the radius of planet X squared, which you should not be so surprised about. All right. Now let's talk about, oh yeah. Okay. All right, let's talk about gravity again in orbits. Now, earlier, what? Don't do that to me. Hold on. Come on. There we go. All right. Ah. Okay. Now, when we figured out the speed that you'd have to throw something to have it go around the Earth, we assumed that we were close to the Earth. So we said that the force of gravity was mg. Well, now, let's abandon that assumption, all right? Now we just want to figure out what that speed is to go around the Earth, but now we can be far away from the Earth. So in other words, we're not going to use mg as the weight, we're going to use Newton's law of gravity for the weight. So let's do that. All right. So here it is, okay? So this is us, this is Earth, and this is something that we're going to throw around the Earth, all right? And we're far, far away. All right, so what's the force of gravity? So I'll just use Newton's law of gravity. So G, uppercase M, that's the Earth. Lowercase m, that's whatever we're throwing around the Earth, divided by this distance, right? So this is from the center of the Earth to the center of the thing. But this is small, so we'll just say r. So r squared. Okay, great. Now, what kind of force is this? This is going in a circle. So what kind of force is this? Centripetal. So like always, we write down the sum of the centripetal forces equals mv squared over r, right? And again, now hold it a second. We have two m's. We have uppercase m, lowercase m. But which one is undergoing the circular motion? The lowercase m. So that's why I was careful. You know, I wrote lowercase m there. Okay? All right. So now we have, so this is true. And now what is the centripetal force? It's that. So it's G uppercase, lowercase over r squared. Okay. So let's solve for v. Let's solve for v. So as always, the mass of the object cancels. Let's see, we're going to multiply that by r, multiply that by r. So that cancels, that cancels, that cancels, that cancels. And now we just want to take the square root. So what we have is we have v equals square root of g, mass of the Earth, divided by r. And there you go. Hey, what happened? I love these computers. Your PC ran into a problem. It needs to restart. Okay, let's kill it.